Tony is a chief systems engineer at L3Harris Technologies in Rochester. On the James Webb Space Telescope, he started in 2003 as the lead systems engineer for integration and test of the telescope, and he finished as the cryogenic optical director in 2017. Tony is now chief systems engineer for the optical telescope assembly of the Nancy Grace Roman Space Telescope. Some of us would have heard of that as WFIRST before it was named its current name. And that's NASA's next great observatory, scheduled to launch by 2027. So thank you very much Tony for being here and for sharing this with us.
Thank you, Bruce. Thanks for having me. So I will not profess to be an image scientist, nor do I even pretend to be one on TV. But I can certainly tell people about the building and testing of the Webb telescope. And so given that, a little bit about L3Harris. The thing I want to mention is I can also give, a lot of people don't realize how big a role Rochester, New York had in the telescope. So this will obviously give some insight there. And just a little bit about L3Harris. We actually started, the group that I'm in actually started a long time ago, back in the Apollo days. Actually started before then, but back in the Apollo days, we had sent 5 space telescopes up to the moon and orbited the moon to take images of the moon's surface to find a landing spot for Neil Armstrong and company. We also built the backup primary mirror for the Hubble Space Telescope, which is now on display at the Smithsonian Museum in the Air and Space Museum. And we built the optical system that's inside the Chandra X-ray telescope, which launched in 1999 and is still in operation today. A lot of our black hole information came from the Chandra X-ray Observatory. And then, as we mentioned, I'll talk about our role on the James Webb Space Telescope. That's in orbit now, and we're currently building the Nancy Grace Roman Space Telescope. So just a quick overview of the purpose of the Webb telescope, although it's been in the news lately, so I probably don't need to spend a whole lot of time on this. But you know, the first challenge to wrap my brain around was understanding that this telescope was being built to see the very first light that existed in the universe. So this is designed to go all the way back to the beginning of light in our universe, back in the beginning of, almost the beginning of time, if you will, for us. It's also built to understand how planets and stars and galaxies are formed. So for a couple of reasons I'll get into, it's an infrared telescope that gives advantages for those types of science. So just to give you an idea of scale, this is actually so this was a mechanical model that we had years ago in the parking lot of the Rochester Science Museum. Rochester Museum of Science. Got that backwards. But you can see people down here. This gives you an idea of size. Getting to some of the reasons why the Webb is designed the way it is. Infrared allows penetration through ducts, as most of you know. And most of the birth of stars and planets occurs as gravitation take over. Stars pulling on dust, bringing it together, and then it condenses to the point of fusion and turns into a star. The JWST goes from visible all the way to the mid-infrared. Roman. The basically Roman telescope is visible to near infrared. And it shows kind of similar infrared range as Hubble, but there are certain advantages to Roman over Hubble. So one of the reasons why Webb is an infrared telescope is that we learned from Hubble, and we expected for Hubble, that the farther away you look in space, the faster things are moving away from us. So if you're looking at light from the beginning of the universe, that was 13 billion years ago, or 13 billion light years away. So sources that far away are moving away from us so fast that when you calculate the Doppler shift for light coming from the sources, the visible light from that long ago, Doppler shifts all the way into the infrared spectrum. So that's one of the big reasons why the Webb is an infrared telescope. So as you take spectrum from those star sources, or spectrum from planets, light going through the atmospheres of planets, and you're looking for things like carbon dioxide and methane, the signature that you would normally see in visible light will be Doppler shifted into the infrared. So the Webb is optimized for that. So anyway, those are the reasons why it's infrared. These are the first images. As many of you saw, President Biden introduced these, and then NASA introduced these. And I'll go into why it was so spectacular for us to see these images, because we knew we were completely successful. But why was Webb so hard? One thing about astronomical telescopes is that you can never make a primary mirror that's too big for the astronomical science. The universe is huge. You're only grasping a very small, tiny steer radian of the photons being emanated from sources in space. So the bigger, the better. The greater the chance that you happen to catch a photon to generate an image. So with Webb, we were dealing with a 22-foot by 26-foot telescope, which is so big that you can get civil engineers involved on the structures that we had to build. So one of the things that you have to realize is that because it was so big, and even though we're going in the biggest rocket available, certainly the safest, biggest rocket available, this telescope was also going to the L2 orbit, which is 1 million miles from Earth. And there are astronomical advantages to that. If you're in solar orbit, you can stare at a certain spot in space for a really long time and capture the picture, whereas Hubble orbits around the Earth. So about every 40 minutes, it's looking at the sun instead of out in space. So there's obvious advantages to being out on a solar orbit. The other one is that, I'll get into temperature in a minute. But so anyway, you have to use up some of the mass launch capacity of the rocket to store a second stage, additional fuel for that second stage to get out to this L2 orbit. So that limits the amount of mass you need to build your telescope even more. So if you look at the blow up here, the part, so this item in the lower right tucks into the center opening of this backplane, and then these are radiators that slip over the top of that. These are thermal radiators. They emit the heat out into space to get the telescope down to temperature. So when this launched, the launch load direction is along this tower at the bottom. It goes up through the backplane in this direction, vertically up and down on the stage. But for building and testing this telescope, we had gravity going horizontally across this page. So because mass was limited, the mass was prioritized to solving loads in the launch direction and not solving loads in our build and test direction. So in our direction, we had a very sagging structure to work with. It did not have enough strength to hold its own weight in a 1G environment. So more about that later, but this is a close-up picture of the instrument module that went into the back part of that back plane. There were three near-infrared instruments. The near-infrared camera came from the United States. It's mostly University of Arizona with some help from Lockheed Martin. Let's see, is this in the, I just realized that's probably been in the way the whole time. The near-infrared spectrograph came from the European Space Agency. We actually mounted the detectors on the near-infrared spectrograph here in Rochester. Another Rochester connection is that the near-infrared detectors, a lot of the research and development for those detectors were done here at the University of Rochester. The near-infrared slitless spectrograph and the fine guidance sensor, this was built by the Canadian Space Agency. And then the mid-infrared instrument was built by a European consortium. That went up to 30 microns wavelength. So black body radiator at 30 microns meant that our telescope had to be down in the down around 400 degrees below 0 Fahrenheit, or about 40, 50 Kelvin. So, you know, in our industry, a lot of times when you talk to vendors and material providers and you talk about cryogenic, they go, oh yeah, we can operate in cryogenic. But almost 85% of the time, their cryogenic is liquid nitrogen temperatures. And, you know, we were operating down at 40, 50 Kelvin for this telescope. And in order to get the telescope cooled down enough during our ground test, our test equipment in our chamber had to get down to 18 Kelvin. All right, so as I was mentioning, I'll play this video where you can see a time-lapse video on us integrating the mirrors onto the structure. So as I mentioned, the mass was optimized in the other perpendicular direction in terms of where gravity goes to maximize the strength in the launch direction. But as you can see, while we're integrating, gravity is perpendicular to the floor here. And we had to integrate these mirrors in the zero gravity location to well under a millimeter tolerance. And we needed precision, you know, of a millimeter. So not only did we have to very carefully calculate where this sagged structure would end up in zero gravity, but as you add on an optical assembly with its mass, or primary mirror segment with its mass, in this case, you have to recalculate the effect of an additional mass on that particular part of the structure and figure out where the new location of the next primary mirror segment goes on, so it ends up in the right spot when it goes up into zero G space. So hopefully, and it went to the wrong screen again. So, so here's some more pictures of us taking the cover off after the primary mirror was completely integrated. and also putting the other optics in, the secondary mirror and the aft optic structure. Here's another shot of the instrument module going into the tight opening on the backside of the that backplane that I showed you. So there was tight tolerance getting that down there, and we also have to deal with region access because the connection between that module and the backplane is at the bottom of that module. So we lower that all the way down in, and then you have to reach through the walls of the backplane to where that connects to make that connection. So one of the things I want to mention that, this project, of course, used thousands, over 1,000 engineers and over 10,000 technicians, assemblers, machinists, et cetera, from all over the U.S., Canada, and Europe, including here in Rochester. So this is a blow up of our area. And this is probably only half the companies in the area that we worked with to put Webb together. We used a lot of the machining, optical assembly, electrical, mechanical assembly, welding, and so forth in the Western New York area to put this Webb telescope together. So given the size of this telescope and the fact that we wanted to simulate at least the thermal conditions in space, even though we couldn't go to zero gravity, we had to use one of the largest chambers available in the U.S., which is the chamber used to test the Apollo lunar module down at the Johnson Space Center. And, since we're below the freezing point of nitrogen and oxygen during one of our early tests, so this chamber is 120 feet tall by 60 feet in diameter. And during one of our earlier tests where we were going cold, we had an air leak. So if you have an air leak in your chamber, then all the nitrogen and oxygen in that air freezes. And when we had that issue, we calculated that in this huge chamber, the air leak we were looking for was a 1/4 inch diameter. So we kept plugging away at the test while a crew, searched the chamber for that 1/4 inch diameter air leak, and they finally found it. But this is the first time I've ever seen solid oxygen and solid nitrogen. So this is what we were doing in the chamber. So on the left, you see the telescope just barely fits within the door. I even had a panic call from NASA that night. They were afraid it wouldn't fit. But, at least 2 years ahead of the time, we had surveyors out to carefully measure this door opening in space. This chamber was built in around 1960. There were blueprints available, but the blueprints didn't necessarily match what the actual hardware was. So back then, they built this whole chamber in a day and then built the building up around it. And in today's processes, there's no way you would get a chamber this size built in a day. And, rather than doing lots of analysis, they just made it beefy, put a door on it. And when the first time they put a vacuum in the chamber, the door dented inward. So they said, okay, guess we got to make the door thicker. So they took the door off, made a thicker door, put it on, and it's been used ever since. So what were we doing in this chamber? This telescope rolls in on rails into the chamber, and just like an optical test table on isolators in your laboratory, you want your test equipment on the same vibration plane as the unit you're trying to test. So we actually lifted this telescope up onto the ceiling, and it was held up by 6 vibration isolators at the top of the chamber. Below that, we were hanging 9 tons of test equipment over this multi-billion-dollar telescope. So we had to make sure all of that worked safely going down to this 18 Kelvin temperature. At the center of curvature of this almost parabolic primary mirror was a optical assembly to measure the quality of the aligned segmented mirror, the optical quality. Underneath that were 3 1.5 meter diameter flat optical mirrors to retro reflect light back through the system to test the rest of the mirrors. And picture to the right, you can see one of the mirrors in place. The other 2 mirrors weren't completed and put in place yet, so those are just mass simulators in there. The other thing that you'll see here are 4 windmills at the top of the chamber. We had photogrammetry cameras on the ends of those windmills. The technique we ended up using for optical metrology in this case was photogrammetry. The slide coming up on that next. So just to give you an idea of the challenges involved, one of the first things that we spent a long time discussing with NASA, they're used to building telescopes on the ground, fully aligned, with the exception of knowing that there would be a gravity change going up into space. And we had to spend a lot of time convincing them that, yeah, it's okay, we'll get this all aligned on the ground, and then we're going to wreck it by folding it up and stowing it, and you'll have to do it all over again in space. And it was a completely different testing paradigm, because it switched from how good is your telescope to how well can you align the telescope in orbit. So there was a lot of work to kind of think through that and convince everybody that when we're done with this testing, it will work on orbit. Also, typically in telescope testing, you have that autocollimating flat descent to retro-reflect light back through the full telescope. Usually it's a full aperture, the same diameter as the primary mirror. But in this case, we're talking about a 22-foot diameter mirror, and we're going to 18 Kelvin. So you need something that's optically flat, 22 feet, and you need to be able to quickly cool it down and stabilize it so you can run your test. And, that's just not doable for a mirror that size. So when you went through the whole verification and testing plan to think through, okay, what exactly is the minimum that we need to test, and figured out a way to do it with 3 smaller lightweighted flat mirrors that were made with borosilicate, which has a flat coefficient of thermal expansion curve at 33 Kelvin. So we heated those up to 33 Kelvin, so it had a nice flat curve for this test. We had to figure out how to do metrology in a chamber at this temperature. I'll talk more about that in a bit. That large sun shield that you saw obviously doesn't fit in this chamber, so we had to work through the thermal verification test scenario to make sure we had a simulator good enough to run this test with the right boundary conditions for the thermal state. We had to inject light in there. I'll talk more about that. You had to know where the test mirrors were. We had to figure out how to test a segmented primary mirror instead of a monolithic primary mirror. Because we were we're testing a telescope made to measure at 40-50 Kelvin. You had to be careful with your black body radiators inside that chamber. Otherwise, you would get a lot of stray light and not be able to do your optical test. Our test equipment had to have better performance than this telescope at cryogenic temperatures in order to test the quality of it. And as I mentioned, nothing could fall on the multi-billion-dollar telescope. So, actually, I'm going to go a little bit out of order. Let's start with photogrammetry. So, for those who are familiar with photogrammetry, you can think of it as taking thousands of two-dimensional pictures from every which angle you can, and then using the parallax effect, doing the reverse math to figure out where points in those two-dimensional pictures really are in three-dimensional space. And to enhance that ability, we put white dots everywhere. You can see some of the white dots on here and out here. This picture in the middle is a purposely oversaturated picture to give a sense of what the photogrammetry camera is looking at when it takes pictures. And I believe Sherilyn will give a talk later for this group on the image processing and across these vast distances to well under a millimeter. So once you know where the mirrors are to within a millimeter, now you need to get it the rest of the way so within a fraction of a wavelength in visible light. So with at least a couple of patents, we came up with, we meaning the Webb telescope group, came up with the idea of using two lasers of different wavelengths and essentially using the B frequency between those two wavelengths and generating an effective longer wavelength out of that B frequency. So we were able to construct this to get a B wavelength of greater than a millimeter. And on top of that, we made one of those laser wavelengths adjustable. So when you start with the 1 millimeter wavelength, your uncertainty is a fraction of that 1 millimeter. Still not good enough to get it visible down to a fraction of the visible wavelength. So we could take a variable laser and adjust that wavelength to get it lined up to within that 1 millimeter band, and then adjust the effect wavelength so it's shorter and shorter and shorter, and step through, move those segments into phase until it was well enough lined that we measure the whole primary mirror with a single visible wavelength. This is just a picture of what this looks like with the thermal blanket all wrapped around. There's a upper level here, and the center of curvature optical assembly would look down through a thermal shutter that we had in the center down to the primary mirror. So one of my pseudo image science pictures in here. So not only was the structure very lightweight, but the mirror segments themselves were very lightweight, and they had tip tilt piston actuators behind the mirrors, and also a radius of curvature actuator behind the mirrors. So a combination of that and gravity. Believe it or not, this picture on the left was the perfect image that we were looking to achieve on the ground. That's with all the 1G gravity effects acting on the mirror, and you do the reverse and you get the perfectly phased mirror in zero gravity. So to get light through the rest of the system, We actually cantilevered fiber optics in the shadow of one of the secondary mirror struts out to the middle of the primary mirror. There's a cast-grain focus here, just above this baffle that goes down into the aft optics and the detector instruments down below. Here's one of the guys connecting those fiber optics to the top of the telescope there to inject light down through the system to the detectors and also up to the secondary mirror, reflect on the primary mirror, retro reflect on those three mirrors up above, and go back down through the whole system. And so that's how we could optically test where the secondary mirror was located, how well the tertiary optics were behaving, and how well the instruments were aligned and behaving. And we could also practice, you may have heard, the whole alignment process on orbit, where they would focus on a star and find where the mirror segments were and do a coarse phasing and a fine phasing. So they step through that whole process using these three flat mirrors. That whole process was practiced on the ground. Not only practiced on the ground, but we also had a connection to mission control in Baltimore to do the commanding from there during this test. Another image processing picture for you. So this is what it looked like. It was not only sub-aperture, but within the sub-aperture, we had three sub-apertures from the different segments. We did that on purpose because of the sensitivity to vibration. Basically used a sharp Shack-Hartman technique to characterize the telescope. The image processing was using phase retrieval, focus diversity phase retrieval. So we capture a nominal focus image and then in and out of focus from that image. And then from those three images, we could determine the pupil wavefront error map. I'm probably close to time. So one of the things that in a project like this, so anyone who has left a Pyrex baking dish on a hot stove burner like I have knows what happens when you heat something up too quickly or cool something down too quickly. You end up with a lot of pieces on the floor. And so for the same reason, there was a limit to how fast we could cool down this telescope and how fast we could warm this telescope up. And it turns out that with this telescope, the fastest we could cool it down was about a month's time. And the fastest we could warm it up was about a month's time. So it's a very intricate test configuration, not only optically, but also thermally. Just a 1 watt leak through a seam and a blanket, or if there were too many thermal sensors that popped off and we were no longer safely monitoring temperature, any of that would have required aborting the test and warming back up and fixing it. So if there's any issue like that, there's an automatic 3-month impact to the schedule. Fortunately, everything worked the first time when we reached temperature, but then Mother Nature decided to throw Hurricane Harvey at us. And so that was added to the adventure. We had to stock up on food and work with a meteorologist on base. We had to kind of time our shift changes between spiral arms of the hurricane passing through. And believe it or not, we only lost a day batting down the hatches and so forth, and then we resumed test. And we actually learned a lot because the telescope and all the systems inside were just put in a holding pattern and reach quiescence over that day. So after that day, when we started paying attention to the test again, started turning things on, we quickly understood any thermal influences to the rest of our testing. Moving on, and then the picture in the middle is just an idea of all the different things going on simultaneously during the test. We were constantly optimizing and re-optimizing and cramming as much testing as we could in the month we had down at temperature, which included a very long thermal balance test. So with that, I'll stop there for questions. As far as links that you can go to, there's sbie.org. There's if you go there and you have access to the digital library, there's lots of papers that go through a lot of the things that I mentioned in much more detail, especially engineering detail. You can also go to jwst.nasa.gov. There you'll find links to the YouTube videos like the one that I showed. There's also a Flickr location with pictures of the building and testing of Webb. There's a blog, blogs.nasa.gov/Webb. That's not about the integration and test. It's more about what's happening today on Webb. And there's also l3harris.com. And as I mentioned, we're in the middle of Nancy Grace Roman Space Telescope. We're also hiring if you're interested, and you can go there if you want to learn more about what we're doing with Nancy Grace Roman. So with that, I'll stop and open it up for questions and answers.
Hi, this is Wayne. I'll ask a quick question. You talked about the thermal stability and the risk of changing temperature too quickly. How does that handled at lunchtime? Yeah. It seems like you have a warm telescope at lunchtime that's going into space, and you don't really have a month for it to change temperatures.
It actually took 3 months to cool down in space. It's actually much. We were purposely driving it faster to save time down here on Earth.
Well, so the point is, it's not happy for operation during the gradient, but it's not at risk of cracking.
Yeah, so in space, it took 3 months to cool down, and also another 6 months to get it aligned and calibrated, and so forth. So by the time real science started, it had very well stabilized at temperature.
I get it. The reason why it took so long is because space is a vacuum, so although the temperature difference was great, the ability to transfer heat was low. Is that a true statement?
Yeah. Also, there were some heaters on the telescope to slow the cool down because they had to worry about contamination from other parts of the telescope, so they would keep certain things hot. Hotter than others, so if there was any contamination, it would go to non-optical surfaces first, then let the optical surfaces cool down. We also, one of the advantages we had on the ground is we could connect straps to the telescope to cool down areas where a lot of heat could be pulled from it. We also had some ground radiators right up next to the hot portions underneath the primary mirror. That was a good heat sink to draw that heat away. So we had certain advantages on the ground to pull heat away from it faster than what could be done on orbit.
Very good. Thank you.
Tony, I want to give you some points for an excellent talk. I mean,
you
went into some of the thermal parts of it that most everybody takes for granted. especially the rate of test, the rate of change that can really stress things. My original roots are a test equipment engineer, so I really found it fascinating that you could delve into that stuff so that everybody could understand it. A lot of people take that for granted.
Thank you.
So, Tony, this is Roger Triplett with a question. Now that the telescope is up in space, were there any surprises with your testing that were not accurate or that you would adjust for next time you do something?
Actually not. We're finding a lot of the behavior in space is exactly how we tested it. The one thing we couldn't do on the ground, of course, was turn gravity off. So, when the pictures came out as a big relief, all those very careful calculations that we did, it was a big relief to say, oh, great, we did that part correct. And it's not just, the complication of you add mass and then you change your structure. So you have to figure out where to add the next mass. We're also, as I mentioned, we work with engineers from Europe and Canada. And so there were additional communication challenges to make sure that numbers we were getting from them, we were understanding correctly how to interpret those numbers and how to use those to figure out the 1G state for their 0G design. And one of the stories I didn't really get into, so this is considered on the ITAR list. So it was really interesting, towards the beginning of this program, when I started working on it, we were told that we were working with Europeans and Canadians, and oh, by the way, you can't tell them anything because they're foreign nationals. So that was really interesting. So we had, and it's the Department of State that controls that, who are not technical people. They're all diplomats, right? So I worked with a person who kind of taught me how to resolve that problem diplomatically instead of logically, which is very different for an engineer. Fortunately, I had enough years to make my way there. Requires a lot of patience and baby steps, but we had enough years that by the time we got to the test, we could actually talk to them.
Not only that, you've got the restrictions on sending hardware back and forth too. Some of that's restricted as well.
Oh yes, absolutely. And it was awkward because they could tell us whatever they wanted. So you'd have a conversation. Oh, it's fine for you to tell me whatever you want about your product. I just can't tell you anything about our product.
Yeah.
So that was fun.
Becomes an information diode.
Fascinating. Thank you very much. Wow.
All right. Do we have more time, or I can certainly tell more stories, but I didn't know if this was 45 minutes or an hour.
I don't think we have a hard limit.
Well, I'll tell you another story.
Yeah,
We can also talk about Roman.
Oh, yeah.
So I'll tell you another story. So this is you see this, and I'll get rid of this. So it's Mexico. We had to build a very large structure to, you saw the video of the robotic arm we used to put those segments in. And we had to build a very big structure to put this in. And you can see these people going around and drilling holes and putting footers into that floor. So there's funny story behind that. In that, so this is a state-of-the-art clean room for large satellites. Right. This is down at NASA at the Goddard Space Center, where they make satellites. And it's a pristine clean room floor, epoxy floor. And we told them, well, we have to build a structure that's safe for an earthquake. You don't want your multi-billion-dollar telescope tipping over from an earthquake. And this was down in Maryland, and some of the people down there had lived in Maryland all their lives, and they're like, I've never experienced an earthquake. We don't need to worry about that. And, there's no way they wanted us to drill holes in their pristine epoxy floor. And so we said, well, okay, if you're willing to make the call and take that risk that there won't be an earthquake while you have your multi-billion-dollar telescope in this stand, then all right, we won't drill the holes. Well, of course, they didn't want to make that call. But they didn't want to put the holes in the floor either. So there were a lot of hemming and hawing. And we had to stay on schedule. So we had a week left for them to make a decision. We told them, look, you've got one more week, and then we need to, if you want us to stay on schedule, we have to start sending our parts and crew down there to drill the holes and put the footers in.
That's the lesser of the two evils.
Okay.
Right?
Right. Okay. We'll have a meeting of all the stakeholders here in Maryland. Lock everybody in a room, wait for the white smoke to come out, and let you know what the decision is. So the meeting was scheduled for
good analogy
for Thursday of that week, and a few of our people were scheduled to travel down there. Tuesday of that week was the biggest earthquake in it was Virginia history, but it was the biggest earthquake felt in Maryland. The center of the earthquake was in Virginia, but they felt it in Maryland. They quickly canceled the meeting and said, "Come on down and drill the holes."
An act of God. I love it. Perfect. Boy, how did you dial that one up?
I know.
Man. Murphy was your friend that day.
Yeah,
That's
really,
right.
you get such
Usually it
clarity.
works the other way around.
That's right.
Just drill the holes.
What's taking you so long? You need a bigger drill?
Yeah.
I love it. I just love it. You think about how many times it's gone the other way. I find that incredible.
Yep. Oh, and of course the other act of God was the hurricane.
Oh, that's got to be a royal pain.
Yeah. So that region, so the Johnson Space Center is right next to the Gulf Coast, and they designed all the roads in that area to be conduits to funnel the water to bayous, and then the bayous funnels the water out to the Gulf, and so they're built to handle tropical storms and hurricanes. And we actually, during one of our practice tests, we had a tropical storm, and so we experienced like the parking lot flooding. And by then, so every hurricane season, we figured out the exact websites to kind of monitor hurricanes coming through, and what track they're likely to take, and the probability and all that. So for this tropical storm, we had it down, and I was working second shift, and another group was working the A shift, but they couldn't go home because this tropical storm was coming through right after the second shift came in, and before they could leave, this tropical storm came through. So we were monitoring the websites, and as I mentioned, there's a meteorologist that works at Johnson Space Center. talking to him, and he could say, okay, you can, at 8:30, the A shift can go home. There'll be a clearing in the
The eye will come over, huh?
the train of rain that's coming through. And because of the way it was designed and give it like 15, 20 minutes for all the water to just low enough so you could drive back to home or the hotel or whatever.
Wow.
That was a one-day tropical storm. So when this Hurricane Harvey was threatening, we were monitoring the websites, and fortunately we realized, okay, it's not going to hit head on. So that means what we're going to have to deal with is the rains, which is like the tropical storm that we went through. And the only difference was the tropical storm was one day. The hurricane, it was the same as that tropical storm, but 5 days in a row. So we had 52 inches of rain. In like the first 3 days was 52 inches of rain.
Wow.
And the emergency management said, no driving in the dark. It was just too dangerous. They couldn't save people necessarily. They couldn't get to you if you needed help, and there's no guarantee there would be enough lighting around, etc. So we quickly switched from 3 shifts a day to 2 shifts a day, and it would literally be the meteorologist looking at the spiral arms of the hurricane and figuring out, okay, what time in the morning do we do a shift change? And then whoever's on the day shift would get a text in the morning, like, be ready to drive in 20 minutes or something like that.
Wow.
And, everybody would, first of all, we all went to the rental car shops and got higher level cars like SUVs and pickup trucks.
Do they rent those amphibious ducks at all?
No, they didn't. But so that's what we do. And then at night, do the flip. You would pick a time before sunset when there was a trough in the rain coming down, and the text would go out. Okay, all the second shift people drive in now, kind of thing.
Wow. Now, what did you do when you got there to the parking lot? You have some way to keep the water out of the parking lot?
Yeah, it would drain out of the parking lot just as quickly as it drained down the road.
Oh, so it wouldn't get
But
very
you would
deep
get in
then.
the building.
Oh, wow.
You would get in the building and look at, go up and start your shift. And if you had a break, you could walk down. And if it's in the middle of the pouring rain part, you would literally see like 1.5 feet of water out in the parking lot. There were a couple people who weren't smart enough to get higher cars that had their the bottom of the cars flooded. So.
Yeah, because in this last hurricane with Ian, my granddaughter goes to Embry-Riddle, which is, if you know what the area is like, that's where the Daytona racetrack is. And her dad says, make sure you park at the hill. There was a small hill there. Make sure you park your cars at the hill. And sure enough, they were the only ones with dry cars. The racetrack and the airfield was literally under 2.5 feet of water.
We had one guy who flew in right before it hit and didn't make it to the hotel in time. So we told him to park. There was a certain Walmart that was up on a relative hill. Houston's pretty flat, but there are relative rises. So he slept in his car at this parking lot at this Walmart parking lot that was a little bit higher than everywhere else. And then the next day we told him when the streets would be clear enough for him to make it in.
Yeah, well, down there, a bridge overpass is considered a hill in some cases.
Yes, that's right.
Excellent. Well, nice job.
Yes, thank you very much.
Thank you.
Yes,
I
thank you.
appreciate it.
That was
Thank you.
terrific.
Tony, can you please go back a few slides to the one, I think one of your last ones. I think it was. Keep going. There, right there. Back one. Yeah, you see that test roadmap, like a Gantt chart kind of thing? Can you
Yes.
expand on that at all?
Yeah. So, a system this complex, you can think of it. So you have thermal experts, you have optical experts, you have electrical experts, you have people on the telescope team. There are 4 instruments, so you have people on each of those 4 teams. You also have the people in Baltimore that are doing the communication part out in this, the mission command stuff.
Yeah.
You have the flight software people, the flight software experts. You have the chamber team. So just to give you an idea of the number of different experts, and you have 3 shifts of this, right? So now we didn't go to Baltimore every day. We just picked certain times where we would do the commands from Baltimore just to prove that link and communication works okay. But all of those different systems have limitations. Certain things have to be a certain way in order for them to do the test that they need to run, or you need to have a combination of items in a certain configuration to run a particular test.
Yeah.
Certain things have to be at the right temperature to move into that configuration, on and on and on. Or if you're doing dark images to calibrate the detector, you have to have any test light sources off,
Or even heat sources.
so on and so forth. So this was kind of the bulk of my job, and I had one helper with me. So he and I, it got so complicated that it basically had to all be in our head, because the stuff you would learn stuff in the test which would completely change whatever plan you had put together, right? So,
well, if you don't mind, can I ask, is that a commercial piece of software that was adapted for that, or what?
Excel. It was done on Excel.
Really great.
Let
me give you the relate of why I'm interested. I teach engineering at RIT in a group called MSD, which is Multidisciplinary Senior Design. And what happens is they're given a project to work on, but it's a team, just like an industry. You got mechanical engineers, software engineers, electrical, all the disciplines. All right. And so they get assigned a project, and they got to develop the concept, the budgets, et cetera, et cetera, et cetera. And so what I'm trying to do is teach them how to do integrated Gantt charts, which is like the piece that you're showing. In other words, each of the guys with their individual disciplines stand up and say what they need in order to do their job. And then you've got to have a coordinator to be able to integrate all of that stuff and make it somewhat sensible. And yourself, when you're in college, number one, you get a lot of book learning. You don't get a lot of hands-on experience. Number two, it's usually all within your discipline, and things outside your discipline are really an ancillary tangent. For example, my background's electro-optics, and so if you got a thing called thermodynamics, it was kind of considered a backdoor elective, if you would. So it is in some cases for a student that's not been exposed to this in real life, they're kind of stretched a little bit. You know what I mean? They're operating like a fish out of water. So that's why I think one of the challenges is, if you had 5 electrical engineers working together, it'd probably work together much easier than mechanical and optical, industrial design, for example, all those other disciplines that can't necessarily relate to the stuff that you're doing. And one of the interesting pieces, I've got a couple of radio telescope projects in the that we're working on. And one of the things that the College of Science likes to say is that engineers and astronomers don't necessarily talk the same language. And the way I used to teach over in the College of Science for a while, and they said astronomers are users of equipment, not developers of equipment. So in some cases, you've got the ding dong to develop something for a person who is not speaking your own language.
Right.
So, just even after you're done doing it, you got things like, well, here's the customer requirements. And you say, okay, here's what I heard you say. Is this what you mean? And they say, oh, no. We want something different. It's almost like a translation where you've got to take their words and put them in engineering speak that's measurable. And that creates a lot of stress right up front.
Yeah, you need a coordinator that can speak multiple languages. So
I was going to say, you need a translator.
Yeah, right.
And being of both the astronomy and engineering community, I was able to build that bridge for some of these guys, but it really stressed them out a lot.
Yeah.
Tony,
in this industry, we have systems engineers to do that.
Yeah.
Yeah, Tony, I was just going to ask, was your company or your group the system integrator for the Webb telescope? Did you do the system engineering for the whole project?
So the system engineering that we had to do was figuring out how to build it. How well did it need to be built, and how well did it need to be tested? How are we going to test it? How are we going to build it? How good did the equipment need to be that we were building it with? How good did the equipment need to be that we were testing it with? We had to come up with all the renovation requirements for this Apollo lunar module chamber in order to do an optical test. It turns out that in the astronaut world, they don't need to be anywhere near as clean as the optical world. So we had to go in and inspect and tell them to scrub the chamber again like 3 times before it was clean enough to be able to put an optical telescope inside. And, so that translated to essentially running this test. So we were the coordinators, besides running all the thermal and optical test equipment. We were also the coordinators for the whole test.
Did you write the specs for the subsystems and hire the subcontractors and basically do all of that?
For the test equipment, yes. Yes, that's exactly right.
Interesting.
Well, that really is system engineering when you think about it.
Yeah,
correct. It is. It's exactly systems engineering. So
and that's probably one of the. I'm sorry. That's probably one of the least known factors in college today. I don't think they pay enough attention to that in terms of discipline and training.
Yeah, it's I think at the undergrad level, I would just give it awareness. You need to be you need to have a degree in one of the disciplines anyway. You need to understand a discipline down to that detailed level. I think of systems engineering as a jack of all trades, expert at nothing. That's not entirely true, but
well, that's not entirely true, but it is. One of the things it is like taking the 10,000-foot level to be able to see the whole picture, yes, rather than a knothole view of the universe.
Right. So in this planning, so just to add to your thinking about planning across multiple disciplines, not only are we planning across multiple teams here and disciplines, but not all of the special teams are there 24/7. So, we had to maintain long-term plans and know when to tell somebody, okay, you need to fly out today to make sure you're, today's Thursday.
Now, were you
we
guys
gotta fly
stationed
out
over on
today
Lee
to
Road?
Make sure you're here on Saturday. Some of us are. Some of us are on Elm Grove Road.
Yeah.
Lee Road is where we make fabricate the large optics.
Right. Yeah, I've been through that
And
facility a number
Elm
of
Grove.
times.
Oh, Elm Grove is where we do the integration and testing and image science.
Well, thank you very much. I need to sign off now. Very fascinating talk.
Okay, glad you appreciated that.
Thank
Thanks
you.
for having me.
Thank you.
Fascinating was an understatement.
Very
All
good,
right.
very interesting.
Thank you.